This call is now being recorded.
Okay, so we have discussed about class A power amplifier. We can say it's also a voltage amplifier. Only the difference is that the load resistance connected, that will be very low value in the case of our amplifier. Then also we are using power transistor instead of normal transistor. We are using power transistor in this case. Okay, and in class A power amplifier, it is the simplest form of power amplifier, and here we are using a switching transistor, that is power transistor, in common emitter circuit, and transistor is always biased on. That is, the conduction angle of class A power amplifier is 360 degree. That's a complete input signal. The complete cycle of the transistor will be on. So the complete input signal will be passed to the output. Okay, and our operating point is fixed at the midpoint of load line. Okay, so this is class A power amplifier. This is simplest configuration. Here we are using the common emitter amplifier with the voltage divider, biasing and bypass capacitor. The same arrangement is used here. We have R1 and R2, that are the biasing resistors, and that are used to fix the Q point. Fix the Q point means we have to fix our Q point to the middle of the load line. Okay, for that purpose we are using this R1 and R2. So by adjusting the value of R1 and R2, you can fix the Q point. Okay, and that resistor RE. What is the purpose of resistor RE? That emitter resistor stabilize the Q point. Okay, so for stabilization purpose we are using this RE, and you will be having a bypass capacitor. Okay, so this is actually our similar to our common emitter configuration. So here the difference is that RL will be very low compared to our normal voltage amplifier. This load resistance value will be very low in the case of power amplifier. And second thing is our transistor. Transistor used will be different. Here we are using power transistor. Difference in the discuss. Instead of normal BC107, we are using power transistor here. Okay. But actually, we can say the maximum possible overall efficiency is 25% here. Okay. And then we have performance parameters discuss. So among that, efficiency is one of the most important parameter. Efficiency means AC power delivered to the load divided by input DC power. That is, main purpose of a power amplifier is to convert the DC power into output AC power. Okay. So that conversion efficiency is the major performance parameter of a power amplifier. By using this configuration, the maximum attainable value of efficiency is 25%. It is also a theoretical value. Practically, that efficiency will be less than 25%. Okay, so normally we are not using this configuration because efficiency is very less here. Okay, here maximum possible overall efficiency is 25%. We can say the quiescent current, that is the Q point current, will flow through the collector resistive load. Okay, here in the collector terminal, that is the point where we are taking output power. Okay, so at the collector terminal or at the output point, we are connecting a load resistor. So the collector current, the quiescent collector current will flows through this collector resistive load, and it will cause a large wastage of DC power. The DC power flows through the collector resistance, cause a DC power loss at the resistor. Okay, so simply at the resistor collector resistor connected. Our resistant across voltage drop or we can say power loss. Okay, so some of the power will get lost at the it is wasted at the resistive load. Because of that, current will flows through DC current will flows through the resistive load, that will cause wastage of power. Okay, so that is why our overall efficiency. So our power waste and our output like power reduce. Okay, it will not be converted into useful power. So our efficiency will get reduced. So our efficiency means output AC power divided by this DC power. Okay, so some of the power will get wasted at the collector resistance. That means it will not be available to the load. So that power lost means our efficiency will reduces. That is the case of normal resistive load class A power amplifier. So in order to overcome this difficulty or in order to improve the efficiency, we can use another configuration for class A amplifier. That is called as transformer coupled class A power amplifier. Okay, actually we can improve our efficiency twice compared to this resistive load. Okay, their maximum possible efficiency was 25%, but in the case of transformer coupled class A power amplifier, we can attain a maximum efficiency of 50%. Okay, it's also theoretical value, it will be less than 50, but however, we can say theoretically that we can attain 50% efficiency by using transformer coupled class A power amplifier. Okay, so simply class actually syllabus syllabus mention class A transformer coupled power amplifier focus but അതിനൊരു ഐഡിയ കിട്ടാൻ വേണ്ടിയിട്ട് ഞാൻ ഈ ക്ലാസ് അതിന്റെ പ്രോപ്പർട്ടീസ് ഡിസ്കസ് ചെയ്യുന്നേ ഉള്ളൂ. ഓക്കെ, വാട്ട് ഈസ് ദ ട്രാൻസ്ഫോമർ കപ്പിൾഡ് എന്ന് പറയുമ്പോൾ എന്തുകൊണ്ടാണെന്ന് പറയുന്നതാണെങ്കിൽ അല്ലാത്ത കേസ് എന്താണെന്ന് നിങ്ങൾ മനസ്സിലാക്കണം. അതുകൊണ്ടാണ് നോർമൽ നമ്മൾ റെസിസ്റ്റർ കണക്ട് ചെയ്തിട്ടുള്ള ഒരു കോൺഫിഗറേഷൻ ആദ്യം ഡിസ്കസ് ചെയ്തത്. അതാണ് ഏറ്റവും സിംപ്ലസ്റ്റ് ആയിട്ടുള്ള കോൺഫിഗറേഷൻ. ഓക്കെ, ഇപ്പോൾ ക്ലാസ് എ പവർ ആംപ്ലിഫയറിൽ യു ഹാവ് ടു നോട്ട് ദീസ് തിങ്സ്. ഹിയർ the transistor will be turns on or conducting during complete cycle of the input signal. Okay, that is conduction angle is 360 degree. So in order to get that, we have to bias our transistor, or we can say our Q point should be at the center of the load line. Okay, so then we are using normal voltage amplifier circuit here. Only the difference is in value of the load resistor RL and the power. Instead of normal transistor, we are using power transistor. Only that difference will be there. Okay, but while we are using resistive load, some of the power, some of the DC power will wasted at the resistive terminal, that is across the RL, that is the resistance connected to collector terminal. There will be power loss, so that our power is wasted. That means we couldn't get useful power at the output completely, so that our efficiency will reduce. So by using this resistive load, maximum possible efficiency is 25%. Okay, so in order to improve the efficiency, we are using another configuration called transformer coupled class A power amplifier. So we can improve the efficiency by twice. That is, we can obtain an efficiency up to 50% in the case of transformer coupled class A power amplifier. Okay, so we focus on actually syllabus. So class A transformer coupled power amplifier. Okay, we can say it is a form of class amplifier, power amplifier, having maximum efficiency of 50%. That uses a transformer to couple the output signal to the load. In previous case, we are directly connecting the load resistance to the collector terminal. Here in the collector terminal, we are using a transformer. Okay, we are familiar with the transformer. So we are connecting a transformer at the collector terminal, and this transformer is used to couple the output signal to the load. That is, we are available with our output signal at the collector terminal of transistor. This is coupled to the load by using a transformer. Okay, normally we are using step down transformer. So you can take the circuit diagram. This is also similar to our complementary configuration. Okay, Complementary configuration is used here. We have two biasing resistors R1 and R2 that is used to fix the Q point, and an emitter resistance RE to stabilize the operating point. And we have a coupling capacitor C1 through which we are applying the input signal. And at the collector terminal, instead of that resistive load, we are connecting a transformer. Okay, so that is why we are calling it as transformer coupled power amplifier. And primary winding of transformer is connected at the collector terminal, and the secondary winding is connected to the load device. That is, we can say it is a loudspeaker. That is why the loudspeaker right load. So we are connecting primary to the collector terminal and secondary to the load. Okay. See here, N1 is to N. Here N1 is to N2. This is N1 is to N2. That is turns ratio. Number of turns in primary and secondary. Transformer N1 is the number of turns in the primary winding, and N2 is the number of turns in the secondary winding. That is why we are this turns ratio is represented as N1 is to N2. Okay. Diagram copy though. Diagram copy though. Okay. Now let us see the explanation for this circuit. So this transformer coupled class A power amplifier is also called as single-ended power amplifier. Since we are using a single transistor here, we are calling it as single-ended power amplifier. And the reason is that configurations more than one transistor is used in it. Only this single transistor, and we are calling it as single-ended power amplifier. That is the other name for the transformer coupled power amplifier. Okay. So we can say basically it is a common emitter amplifier configuration which uses a power transistor. Okay. And the components R1 and R2. R1 and R2 are used to bias the transistor, that is in order to fix the Q point to the midpoint of the load line. Okay. And RE is used for stabilization. And Q point is selected near to the center of the load line. And we can say output current, since the Q point is at the center of the load line, output current flows through the complete cycle of input signal. That is, conduction angle is 360 degree. And the load is coupled using a transformer at the collector terminal. That is, we are coupling the power to the load using a transformer. Okay, so this is about the circuit arrangement. And now, first of all, we can say how the efficiency is improved here. Okay, so the reason is that we are connecting the primary winding of the transformer to the collector terminal. Right. This primary of transformer has negligible DC resistance. Okay, so the resistance value, effective resistance value of that winding will be very less. So we can say the power lost the primary winding will be also negligible. That is, instead of RL, instead of load resistor, we are connecting the primary winding of the transformer to the collector terminal. And this primary winding of the transformer offers negligible DC resistance. The resistance value will be less. As a result, we can say there will be negligible DC power loss at this point. Okay, we can neglect the power loss. That means DC power loss will be negligible and AC power is magnetically coupled to the load. So by using transformer, the AC power is magnetically coupled to the load. Okay. And by adjusting the turns ratio, that is N1 is to N2. N1 is to N2 is the turns ratio, or we can say N1 by N2 is the turns ratio. That is number of turns in primary divided by number of turns in secondary. By adjusting that value, that is by using proper transformer, the source and load impedance can be matched for maximum power transfer. What is this maximum power transfer theory says? The maximum power will transfer to the load if the load resistance equal to the source resistance, right? Okay. So here we can transfer maximum AC power to the load if our load resistance is equal to source resistance. That means for this impedance matching, here load resistance, for this impedance matching, we can adjust the turns ratio. Okay. The equation which by using this turns ratio, by changing this turns ratio, we can change the impedance so that we can obtain the condition for maximum power transfer. Okay. Maximum power transfer will occur when load resistance equal to source resistance. So by adjusting this turns ratio, we can match the impedance. Okay, for the maximum power transfer condition. Okay, so impedance matching is possible by using this transformer, and thus we can obtain maximum power transfer. Okay, so we can see the relation between for this impedance matching. That is, power transfer will be maximum if the amplifier output impedance equals the load impedance. Okay, so how it will get equals? We can say a transformer can increase or decrease voltage or current level according to the turns ratio. So this impedance will depend on voltage and current. As you know, R is equal to V by I. Okay, so according to this voltage and current, we can change the impedance, right? So by since the transformer can increase or decrease the voltage or current level according to the turns ratio, by changing the turns ratio, we can change the impedance also. Okay, so you see the relation. Here we are considering a transformer. Okay, so this is the primary winding of the transformer, and this is the secondary winding. This is primary, and this is secondary winding. And let us say the turns ratio is N1 by N2. Okay, let turns ratio A is equal to N1 by N2. Okay, that is N1 is the number of turns in the primary, and N2 is the number of turns in secondary. Okay, and let V1 be the voltage at the primary terminal, and V2 be the voltage at the secondary terminal. Okay, and I1 is the current flowing through the primary winding, and I2 through the secondary winding. Okay, and also you can consider the impedance. Here RL is the load impedance. That is, actually we are connecting the load to the secondary, right? So RL is the load impedance, and RL dash, I am assuming RL dash is the impedance offered by the primary winding. Okay, so you just note this diagram. Is we are here, you are considering a transformer with the turns ratio N1 by N2. Okay, so number of primary windings is equal to number of turns in primary winding equal to N1, number of turns in secondary winding equal to N2. So we are using this transformer, and V1 and I1 are voltage and current at the primary terminal, V2 and I2 voltage and current at the secondary terminal, and you have impedance. RL is our load impedance, which is connected to secondary, and RL dash is the primary impedance of the primary winding. Okay, now we can say, see the transformer relation. Transformer relation is equal to V2 by V1 is equal to N2 by N1, right? And I2 by I1 is equal to N1 by N2. That is, this is the voltage relation at the primary and secondary, and this is the current relation. That is relation of this voltage and current related to what the turns ratio N1 and N2. Okay. Now, as we already taught, maximum power will transfer to the load if but the output impedance equal to the load impedance R. Right. Now we can get an expression for that. That is, we have this voltage and current relation, as I already told, and that impedance Let RL dash is the resistance or impedance looking into the primary. Looking into the primary, and RL is the resistance of the load or load resistance simply. Okay. Now we have this RL dash equal to what? Here RL dash is the impedance looking into the primary. Okay. So we can say the voltage at the primary is V1 and current at the primary is I1. Right. So I can define RL dash is equal to what? V1 divided by I1. And RL, that is the load resistance at the secondary. So at the secondary terminal, the voltage is V2 and current is I2. So I can say RL is equal to V2 divided by I2. Right? Now I am taking the ratio of these resistances or impedances, that is RL dash divided by RL. Okay, RL dash divided by RL is equal to what? RL dash is equal to actually V1 divided by R1. And RL is equal to V2 divided by I2. Okay. Now I can write like this. ഇതെങ്ങനെ വരും? From this expression, I can write V2 by V1 is equal to what? N2 by N1. Okay. So V1 by V2 is equal to what? N1 by N2. So instead of this V1 by V2, I can write N1 by N2. Okay. And I2 divided by I1. Okay. So what is I2 divided by I1? It is equal to N1 by N2. So I2 by I1 is equal to N1 divided by N2. So I can write this is N1 divided by N2 the whole square. That is N1 square divided by N2 square. Or I can write N1 divided by N2 the whole square. So RL dash divided by RL is equal to N1 by N2 the whole square. Okay. This N1 by N2, this is termed as the turns ratio. Okay. A. That is, I can write RL dash divided by RL is equal to A square, where A is equal to N1 by N2. It is called the turns ratio of the transformer. Okay. So RL dash divided by RL is equal to A square, or we can say RL dash is equal to A square into RL. Okay. So this is the impedance relation of the transformer coupled power amplifier, or we can say at the collector terminal, the impedance relation will be like this. RL dash is equal to A square into RL. Okay. So ഇതിൽ നമുക്ക് implement ആവുന്ന കാര്യം എന്താ വെച്ചാൽ for maximum power transfer from load to collector to load, the load resistance should be equal to source resistance. So we can change, it depends upon the turns ratio. So by adjusting the turns ratio, we can obtain impedance matching. Right. By adjusting the turns ratio, or by selecting the transformer with a suitable turns ratio, we can obtain impedance matching, so that maximum power can be transferred to the load. Okay. So the impedance transformation is given by RL dash. RL dash is equal to what? A square into RL. Okay. So that's what we told is we can transfer maximum power if there is impedance matching. And now coming to the circuit operation, you can see the characteristics. That is, here in the circuit, actually our winding resistor, that is primary winding. In normal transistors, that is in normal amplifier operation, in normal amplifier operation, we have collector resistance here RC. Okay, and we are obtaining the load line like this, DC load line like this, and the slope of this load line is equal to -1 by RC. ഇതൊക്കെ മുന്നേ ട്രാൻസിസ്റ്ററിൽ പറഞ്ഞിട്ടുള്ള കാര്യങ്ങളാണ്. Slope of the load line will be equal to -1 by RC. This is in the case of normal voltage amplifier. Here, instead of this RC, we are connecting primary terminal of that transformer, right? So here, the winding resistance determines the DC load line. That is, this DC load line, slope of the load line depends upon the winding resistance. Okay. As we already told, the winding resistance of this transformer will be very small. Okay, so this RC very small means the slope will be infinity, right? RC very small means the 1 by RC, it will be very large. Or we can say ideally, if RC is equal to ideally 0, then our slope will be infinity. Okay, that means we can say our DC load line will be a vertical line. So normally we are drawing DC load line like this. Okay, but in the case of this transformer coupled class A power amplifier, we can say, since we are connecting, instead of collector resistance, we are connecting primary winding of the transformer to the collector terminal. So actually the load line depends upon the winding resistance of that winding. This value will be very small, so that we can obtain a vertical load line. Okay, so here you can see this is our DC load line, this vertical line, right? This vertical line is the DC load line, and this is the AC load line. Okay, and we are fixing operating point at this middle of load line. Okay, so this is our operating point, and this is the quiescent voltage and current, ICQ and VCQ. Okay. Now that is the DC condition. That is about DC condition. And now if we are applying an input AC signal, to the base terminal of the transistor, the collector current will vary. And when AC signal is applied to the base current IB changes, and collector current IC is equal to what? Beta into IB. So according to the changes in base current, the collector current varies. Okay, around the operating point. That is, we can say around the operating point, the collector current will flow, or we can say operating point will move up or down. And operating point can move up or down depending upon our input signal. Okay, so when an input signal is applied, we can say collector current fluctuates from maximum value to minimum value. This is the collector current signal. It fluctuates from maximum value to minimum value. Okay, and we can say similarly, the collector voltage variation, that is DC variation, will be like this. Okay, so we are fixing our operating point here, and when we are applying an input signal, our base current changes accordingly. Our Q point moves upward or downward direction, or we can say our collector current will changes. That is fluctuates from between minimum and maximum value, and also the voltage VC will fluctuates. Okay, and we can say this variation in collector voltage. Okay, this variation of collector voltage appears across the primary of the transformer. So collector current and voltage and the variations that appears across the primary of the transformer, and this change in voltage in the primary will induce a AC voltage at the secondary of the transformer, right? So according to the variation at the collector terminal, a voltage will appears across the primary of the transformer, and as a result of this voltage, we can say an AC voltage will induces. Okay, by mutual induction, an AC voltage will induces at the transformer secondary. That means an AC power will be developed, which is supplied to the load. Okay, so that is how the power developed across the, or we can say the DC power at the collector is transferred to the load. Okay, or we can say the DC power from the supply. DC power from the supply is absorbed, and that power is given to our input AC signal. Okay, that is how we got a very high signal at the output terminal. Okay. Now we can see the efficiency of this class A amplifier. Theoretically, we can say it is 50%. So how will you obtain that 50% is in an ideal transformer, there is no voltage drop in the primary. Okay. In ideal transformer, there is no voltage drop in the primary. That means at the collector terminal, we are connecting this primary, right? Here it is VCC, supply voltage, and here we have this VCE, right? So ideally, we can say there is no voltage drop across this primary winding. That means this complete VCC will be drop across the transistor. Or we can say this VCEQ is equal to what? The supply voltage VCC. Normally, ഇവിടെ resistor ആയിരുന്നെങ്കിൽ എന്തായിരുന്നു equation വരുന്നത് നമുക്ക് VCC minus ICRC minus VCE equal to 0 ആയിരുന്നു. Or VCE is equal to VCC minus ICRC ആയിരുന്നു അല്ലേ? Normally, if you are using a resistive load. But here we are using a transformer winding so that here there is no voltage drop in the primary. We can say our VCE will be equal to what? VCE. So VCEQ will be equal to VCC. Okay, so complete supply voltage will be obtained across this collector emitter terminal. That is, we can say input power to the transistor will be equal to the power drawn from the supply. Okay, the complete power input to the transistor becomes equal to the DC power drawn from the supply. Okay. So we can write power input to the transistor. Power input to the transistor, that is, will be equal to input DC power. Okay, input DC power, which is equal to what? Total voltage drop into the transistor is VCEQ, right? Actually, it is VCEQ into ICQ. This is the power input to the transistor. Okay, so power input to the transistor is equal to VCEQ into ICQ. But since this VCEQ is equal to what? VCC, I can say the power input DC input power to the transistor is equal to VCC into ICQ. Okay, so input power to the transistor is equal to VCC into ICQ. And in order to find the efficiency, what is the equation for efficiency? Actually, our efficiency is equal to output AC power divided by input DC power. DC power to AC conversion. So efficiency is equal to output AC power divided by input DC power. So we have obtained this input DC power, that is VCC into ICQ. Now you have to get the value of this output to AC. Okay, so we can write output AC is equal to actually VRMS into IRMS. Okay, so we can say at the output terminal, the RMS voltage will be equal to VCC divided by root 2 into this ICQ divided by root 2. By considering the AC power, we have to take RMS values. So that is equal to VRMS equal to VCC by root 2 and IRMS is equal to ICQ by root 2. So I can write this P out is equal to what? VCC into ICQ divided by 2. Okay. Now coming to the efficiency. So I can write efficiency equal to AC output power divided by DC input power, right? So AC output power, now we have obtained is VCC into ICQ divided by 2, right? All divided by DC input power is VCC into ICQ, right? So this VCC into ICQ get cancelled and you will obtain 1 by 2. Okay, normally efficiency will expressed in percentage. So into 100 will be there. So 1 by 2 into 100, that is 0.5 into 100, you will obtain 50%. Okay, in percentage, efficiency will be equal to 50%. This is actually a theoretical case. Okay, practically efficiency will be around 30% by using transformer coupled amplifier. Practically efficiency will be 30%. Okay, theoretically we can say efficiency equal to 50%. Okay, clear ആണോ ഇത്രയും കാര്യങ്ങൾ? Okay. ഒരു problem, ഒരു question എഴുതിക്കോ. A transformer coupled class A power amplifier. A transformer coupled class A power amplifier supplies power to an 80 ohm load. 80 ohm load connected across the secondary of a step down transformer having a turns ratio 5:1. Determine the maximum power output for a zero signal collector current of 120 milliampere. Okay, just ഒന്ന് നോക്കിക്കോ. തന്നിരിക്കുന്ന പാരാമീറ്റേഴ്സ് ഒന്ന് നോക്കുക. You have RL is equal to 80 ohm and the turns ratio A is equal to 5:1. Okay, or N1 by N2 is equal to 5:1. And what is the zero signal collector current? Zero signal collector current means DC condition without applying any input signal. That is ICQ. Okay, this is equal to 120 milliampere. So these are the given parameters. ഞാൻ എഴുതിയ ഇക്വേഷൻ കണ്ടായിരുന്നോ? ക്വസ്റ്റ്യൻ കംപ്ലീറ്റ് ആയിട്ടില്ല.